Okay, what did you get for the limit as n approaches infinity of 8n squared plus 12n plus 4 over 3n squared? You may remember from our previous Pencast that the degree of the numerator and denominator are the same, so the answer is just 8/3. But if you do the math, we would divide top and bottom by the highest power of n. That's in the denominator. You always want to divide by the highest power of n in the denominator. That would be n squared. So I would get the limit as n approaches infinity, 8n squared over n squared is just 8. 12n over n squared plus 4 over n squared over 3n squared over n squared is just 3. So I get 8 plus 12 over n plus 4 over n squared over 3. Now, when n gets big, 8 is staying 8. 12 over n is going to 0. Remember, when n gets bigger and bigger and bigger, 1 over n is going to 0. So 12 over n would be going to 12 times 0. Maybe I better write that out. Limit n approaches infinity of 12 over n is 12 times the limit n approaches infinity, 1 over n. What's this limit? That's a basic building block, that's 0. Because we're dealing with 1/10th, 100th, 1,000th, 1,000,000th. Those numbers are going to 0. What's 4 over n squared doing when n gets big? Well, if 1 over n is going to 0, then 1 over n squared would be going to 0 even faster. Get 8/3. So the exact area underneath this graph y equal x squared on the interval 0 to 2 is 8/3, which is 2 2/3. Let's see if that's reasonable. Let's try to count squares. Let's try to count 1 unit squares. So we have maybe a half a square here. And we have a whole unit square here, so that's 1 1/2. We've almost got another square here, but not quite. So that's not 2 1/2. It's not as much as 2 1/2. Plus we have some more up here. 2 2/3 is reasonable. And when we approximated, remember when we, in the last lesson, when we approximated this exact area, we found it to be between 7/4, that was using left-hand endpoints, and 15/4 was between using right-hand endpoints. So where does 8/3 fit in between here? It had better. 8/3 is what? If you want to write that as fourths, well, let's write it as 12ths. That's what? 32/12. And 7/4 is 21/12. And 15/4 is 45/12. And look, our 32/12 does fit in between here. This all makes good sense. Okay, our next lesson will be defining what we mean by a definite integral. Next lesson will define what we mean by a definite integral. It means something very different from an indefinite integral or an antiderivative. In fact, what you just did, this four-step process for finding exact area under the curve, you evaluated the definite integral from 0 to 2 of x squared dx. But we've got to define what we mean by this in the next lesson. And then, in the next lesson, we'll learn why you would call this a definite integral, how it's related to an indefinite integral, and how is an indefinite integral or an antiderivative related to a definite integral. That'll be the fundamental theorem of calculus, and that'll give us the shortcut for evaluating this definite integral. I'll go on and tell you the shortcut. Fundamental theorem of calculus says to evaluate this definite integral, you just find an antiderivative, so you get x cubed over 3, and you evaluate it at the endpoints. So that's 2 cubed over 3 minus 0 cubed over 3, which is 8/3. It's what we got here. So, just trying to show you where we're headed. Remember, we've spent a lot of this semester finding shortcuts for derivatives. We spent some time at the beginning with the definition of the derivative. Today and tomorrow, we're looking at the definition of the definite integral. And again, we'll have to use the definite integral notation tomorrow. We didn't use that today except here at the very end. And then we'll learn the shortcuts for evaluating definite integrals. But I've just told you the shortcut. It's find an antiderivative of the function you're trying to find the area under. Plug in the endpoints, subtract, you've got it. We need to see why all that works. That's where we're headed for the rest of the week.